So in this part we shall study about the power, density, spectrum of the discrete time periodic signal. Now, if x of n is a periodic, or rather discrete time periodic signal with a period of n, then the average power of the signal p of x is given by 1 over n summation that goes from 0 to n minus 1 x of n whole squared. Now this equation is quite analogous to the average power equation for a continuous time signal, only difference being that instead of the integration we are taking a summation. Why do we do that? The case being that is, in case of continuous time signal, the signal looks something like this. So if we take an integration, say from 0 to t, we can definitely define an area under this. But our discrete signal does not look something like this. It looks like various samples. Like this may be a discrete signal. So what I mean to say is that if we even want to take the integration, we cannot, because these points are discrete and we cannot calculate a definite area under this point. That's why what we need to take is the summation of these values, which will work as an integration in this case. Now let us derive an expression for p of x in terms of the Fourier series coefficient c of k. So we got p of x to be equal to this. So p of x we can write 1 over n summation that goes from n equals 0 to n minus 1. X of n squared can be written as x of n times the conjugate of x of n. And let us expand it a bit further. N which goes from 0 to n minus 1. Keeping x of n as it is, if we expand x conjugate of n with the synthesis equation, it looks something like this. The running sum of k which goes from 0 to n minus 1. The Fourier series coefficient of course will be ck star e to the power jk n twice pi over n. Now reshuffling the order of the summation, this equation becomes summation of k which goes from 0 to n minus 1 over n, since depends on is an independent quantity, or rather a constant quantity. It can be taken inside or outside the summation sign. It does not hamper the result. What we can also do is take c of k outside as well, but not outside of the summation, because c of k, its value depends on the value of k, and the remaining summation looks 1 over n summation n which goes from 0 to n minus 1. The rest becomes x of n e to the power minus j twice by k of n over n. Now moving on to the next line. Here the summation remains as it is, k equals 0 to n minus 1 c of k conjugate. If you look closely, this equation is nothing but an analysis equation, and this becomes c of k. So this term can be written as c of k. So moving forward, this equation can be further expanded to c of k conjugate with its unconjugated counterpart becomes c of k squared. We basically did this work, this step in reverse. So from here we can write p of x to be equal to 1 over n summation of n, which goes from 0 to n minus 1 x of n squared, is equal to the summation of k, which goes from 0 to n minus 1 c of k squared. This is the value of the average power, or otherwise known as the Parseval's relation for discrete time periodic signal. Now the sequence of c of k squared, the sequence that is found from k of k squared, c of k squared, where k equals 0, 1, 2 and goes on to n minus 1, is the distribution of the power as a function of the frequency. What I mean to say that is, if you want to plot the power of a signal as a function of frequency along the frequency axis, you just need to determine the Parseval's relation and plot the respective coefficient of that relation. Hope the power density spectrum of discrete time periodic signal is quite clear, and with that we have come to the end of the theory part of the lecture. Now we will go ahead and solve some mathematical problems of discrete time Fourier series.